Hello everyone, welcome to my channel Maths with Smart Tips. Today in this video we are discuss the steady state solution of heat equation and inhomogeneous heat equation. That is how we can solve the inhomogeneous heat equation and how can we find the steady state solution of a heat equation in 1D. That is first dimensional one-dimensional heat equations. If you like the content, then please give a like to this video, share with your friends, and don't forget to subscribe the channel. So let's start. First, we consider a heat equation, that is ut equal to uxx plus hx, where the boundary conditions are u0t, this is equal to a, and u_lt, this is equal to b, and here 0 less x less equal to l, this l, and t greater than 0, and the initial condition is ux0, this is equal to fx. So this is the suppose the heat equation 1, and this equation 1 describes the heat flow with time independent source hx, and the temperature is fixed at both the end point with different value. That is, this A and B are the fixed at both the end point with the different value and approaches to a steady state solution or equilibrium position. So here our main motto is, we have two motto. The first one is to describe the limit as t tends to infinity for the heat equation, and number 2 is to solve the inhomogeneous heat equation. The main point of steady state solution is the steady state is a solution which is independent of time. This which is independent of time. Now first look at the equation ut equal to uxx plus hx, taking t tends to infinity, taking limit t tends to infinity. For the heat equation ut vanishes, therefore the remaining equation is 0 equal to uxx plus hx, 0 less equal to x less equal to n, and t greater than 0 suppose, and the boundary condition reduces to u0, this is equal to a, and u12, this is equal to b. Since this u is now is time independent, for t tends to infinity the ut term vanishes, therefore this is clearly an ODE. So then we can solve easily by using these two boundary conditions. Just we solve this ODE to get the solutions, which is the good way to tackle the inhomogeneous heat equation. Now we come to the point, the solution procedure of steady state solution or inhomogeneous heat equation. So solution procedure. The solutions procedure. So let us first take the solution. Let Wx be a time independent solution. So this satisfies the heat equation, so we can write Wxx, this is equal to Uxx, or you can write Uxx equal to Wxx. So Uxx, this is equal to Wxx, and W at t, this is equal to 0, since W is time independent. Therefore from equation 1 we can write 0 equal to Wxx plus Hx, and 0 less equal to x less equal to L, and W0 equal to A, and WL, this is equal to B. Therefore this is a clearly a second order differential equation, and we can easily solve this by using these two boundary conditions. Consider the difference Uxt, this is the original solution and this is the time independent solution. Let us take this is equal to V of xt. Integrate with respect to t partially, then we get ut, this is 0, this is equal to vt. That means ut equal to vt, and uxx equal to, we can write uxx minus, if we differentiate this equation partially with respect to x, this is equal to vxx. This implies uxx, this is equal to vxx plus wxx. Now wxx means, from this we can write wxx means minus of hx. So this is equal to vxx minus hx. This we can write. Therefore we can write uxx plus hx, this is equal to v of xx. This. So if we put these two, this and this, then we get vt, this is equal to v of xx, and v0t, this is equal to 0, and vlt, this is equal to 0. 0 less equal to x less equal to L, and t greater than 0 and t greater than 0. This is the boundary condition, t greater than 0, and the initial condition is vx0, this is equal to fx minus limit t tends to infinity u of xt, this function. So we note that the given inhomogeneous PDE reduces to a homogeneous PDE by using this. Then we can easily solve this problem. Now take an example to find the steady state solution. Let us consider the equation ut equal to uxx plus x, where x 0 less equal to x less equal to 2 and t greater than 0. The boundary condition is u0t, this is equal to 0, and u2t, this is equal to 5 at t greater than 0, and ux0, this is equal to fx. So this is the equation. Now we solve this equation. So let us first take to the question is find the steady state solution. So we know that steady state solutions means time independent solution. So how can we solve this problem? So let us take Wx be a time independent solution. Since Wx is a solution, then Wx satisfies the given equation. So we can write uxx, this is equal to wxx, and wt, this is equal to 0, since w is time independent. And also the boundary condition reduces to w at 0 equal to 0 and w at 2 equal to 5. This is the boundary condition. Therefore if we put these values in the given equation, then we can find this wxx, this is equal to minus x, this this implies, so this is clearly a differential equations of order 2. If we integrate 2 times, then we can find easily the solution. So wx integrate once, this is equal to minus x square by 2 plus integrating constant suppose a, and integrating again w equal to minus x cube by 6 plus ax plus b, second integrating constant, and we have these two boundary conditions, so we apply this. So w0 equal to 0, this implies b equal to 0, and w at 2 equal to 5, this implies, so 5 equal to minus 8 by 6 plus 2a, this, and b means 0, so this implies 2a, this is equal to 5 plus 8 by 6, this is equal to 38 by 6, this implies a equal to 19 by 6. That means the steady state solution is wx, this is equal to minus x cube by 6 plus 19 by 6 x, this. So this is the steady state solution. Also you can find, you have to find the particular value for particular x, since this question comes in GATE 2022, this type of questions you have to find the value of w1 or 2 for the particular value of x. So how was the video? If the content is helpful, then please give a like to this video, share it with your friends and subscribe the channel. Thank you friends, see you again in the next video.